Hello friends, uh, let's continue with examples that we started last time. So my next example, I think it would be the part E, would be about fx module. So suppose you have a vector space V over field F. Then from here I'll try to say make a module V over ring fx. So first, what is fx? So fx is, so let's just typically write an element here. So a typical element would be f1 a0 plus a1x plus a2x squared dot 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 an xn, where ai belongs to f. So consider all such polynomials in x whose coefficient lie in f. So that is our fx module. So this itself is a ring. That's not an fx module, that is an fx ring. Now how do you define a ring action over f? A ring action of fx over v. So you already have action f over v, which is given to us. How do you extend? So we'll just digress a little bit. Consider a map from v to v t. Now you can also consider, you can think of t square as a map from v to v, where it's basically applying t twice, and so on and so forth. Tn also same way. So given a linear operator, you can define its square, cube, etc, etc. So to define a group action, what you do is, so if I say ki suppose a0 plus, if I want to act a1 not plus a1x on element v, I'll first act a0 on v, which is the usual, and then what I'll do is I'll just act, because x, I'll replace x with a t and then apply. So given t, so alongside fx, you substitute x with t. So in this way we can define an action of ring fx over say group v, which will be a module. In this way we can define an action. For that we also need to know operator, linear operator t. For different linear operator, the action will look different. So this is the main thing. So yes, this is the fourth thing. So there could be many actions. Next we look on module homeomorphism, module maps and homeomorphism. So we say, suppose there is a map between m and m. We say it is a homomorphism if m plus m1 plus m2 is equal to phi of m1 plus phi of m2, and similarly phi of r of m equals to r phi of m. We'll say kernel of phi is equals to m, such that phi m equals 0. Fine. So now consider this set of all homomorphism between m and n over r. Sorry, not this r. we'll show that this is also a ring. And not just that, we can then talk of module over this ring. Pardon me, over not this ring, this will be a new set, will be module over R ring. So this, so with with a ring R, you can construct a new module. Given two modules, you can construct another module like this. Now we define a quotient of a ring. Quotient ring, not quotient ring, quotient module. So if M R module n submodule of M, then you define M quotient M as R of x plus n equals to Rx plus n. So how is this independent of representation? It's because n itself is a module, so if I had expanded it, it would have been Rx plus Rn. This itself is a n, so this is independent of representation, and then you have a well-defined entity. So this is how we define quotient module. Now we have isomorphism theorem. So if I say if M is a surjective, then kernel phi is isomorphic to n. Or more specifically, if this is just a general map, not necessarily surjective, then n kernel phi is isomorphic to phi of M. Okay, this is the first isomorphism theorem. The second isomorphism theorem is the sum n. So if A plus B, if A and B are some modules of M, then A plus B is isomorphic to A intersection B. Okay. Going forward, a third isomorphism theorem says that you can do some sort of cancellation. So suppose you took M by N and N by K, this is isomorphic to M by K. This is the thing. And the fourth one says that suppose you have M and N and you have constructed M modulo N, and consider A module which contains N, then there is a one-to-one corresponds between all such modules that contains N and all submodules of M by N, which is a submodule of N by N. These are the four isomorphism theorem. I think this is it. We'll see you in the next video. Thank you.